Okay, so here we'll talk about two equipment called ammeter and voltmeter. Ammeter and voltmeter. Actually, in the lab you already use it. Okay, but actually an ammeter is actually, yeah. So here it says yeah. Yeah, an ammeter is an instrument used to measure the current. Okay, ammeter used to measure current. And actually, for voltmeter, it's used for measuring potential differences or voltage differences. Okay, so actually, you can see here is like so this A means the ammeter, this V means the voltmeter. Okay, so we need to connect it correctly so that we can get the correct value. Okay, so here the idea is that for the ammeter, you need to series it with the current you want to measure. Let's say you want to measure I here. Originally the circuit is look like this. The circuit look like this is E, this is small r, and then this is R2. Originally, the circuit only look like this. Here we have I, and then we have V, let's say this is V1, like this. Okay, we would like to measure the current going through this loop, and then we would like to also measure the voltage difference across the resistance R1. Okay, so we try to connect this ammeter in series with the current you like to connect. Okay, actually you don't need to measure them simultaneously. Maybe when you measure the current, you just disconnect this part, and then you can still maybe it will be I think it will be better. Okay, you try to just measure the current for this loop, and then you only series with it. You don't try to connect it to others, because you connect something to the circuit, you may influence the circuit itself. Even though you only connect the ammeter to here, you will still decrease the current a little bit. Yeah, because actually for the current for the ammeter, it should have a small resistance. Okay, here it says this is the resistance RA. RA means the intrinsic resistance of the ammeter. Okay, it should still have some resistance. So the resistance of the ammeter be very much smaller than the other resistance in the circuit. Otherwise, you will decrease the current a lot, which means that this is okay. Okay, this one will have another intrinsic resistance. Oh, it already use R. So let's say this is RS, okay, or RA. This is RA. So RA. So it means that RA should be much smaller than R, or smaller than this thing, because originally I will be like E times 1 over R plus R1 plus R2. Okay, but after you connect this ammeter there, the I will change to, let's say, I prime will be E times 1 over R plus R1 plus R2 plus RA. Okay, so it will actually decrease the current a little bit, because it make the denominator a little bit larger. So it asks you to guarantee that the resistance RA is to be much smaller than other resistance. Okay, if RA is very small, much smaller than the others, then yeah, the influence here will be really small. And then the next step is to measure the voltage V1. Okay, this is V1. We would like to measure it. Okay, actually when you measure this one, you can just disconnect and then short it, and then this part will not influence. Okay, so here when you try to measure the voltage, you need to connect the voltmeter parallelly to that part. Okay, so the voltmeter should connect to node C and node D to measure the voltage difference. Okay, so here it sets the RV of the voltmeter must be much larger than any resistance of the circuit element across. Okay, so of course it should have a resistance RV. Okay, so when you just connect the circuit like this, it will look like this is E, this is small r, and then we have R2, and then you have R1 here. And then after you connect the voltmeter, it's just like you connect RV parallel with the point you connect. Okay, so other part doesn't change. This part will become R1 parallel with RV. Okay, so this value is actually R1 times RV over R1 plus RV, or maybe we can just divide RV on top and bottom. It looks like R1 and then R1 over RV plus 1. Okay, you just divide RV. Okay, so you can see that if RV is much larger than R1, then this will be tends to 0 if RV is much larger than R1. Okay, so this is 0, this is 1. Okay, so it turns out to be 1. But if RV is not large enough, this one will not turn to 0. This will be a small value and then add it with 1. So it will be 1 point something. Okay, 1 point something. Okay, so R1 divided by 1 point something will be slightly smaller. So it will actually increase the current. It will just divide the current. Some of the current will go through that. So if RV is large enough, then there will be no current going through this part. Okay, so all the current going to that part. It will make the voltage smaller. If RV is not large enough. Okay, so that's the idea for ammeter and voltmeter. Okay, so the next part is the RC circuit. Okay, so here, as much as we have a supplement how to solve the constant coefficient ODE, so we may be able to explain why this equation look like this. Okay, so actually it says at the very beginning we have RC in series, and then we have node A and B. This is a switch. This switch can connect to either part A or part B, or completely open. Maybe completely open is also an option. But actually for this circuit, at the very beginning, let's say T is smaller than 0. T is smaller than 0. It just connect to this point. Okay, let's say this is a ground. So let's say this is T is smaller than 0. T is smaller than 0, then it connects to the ground. Okay, so it will discharge all the charge on the capacitor. So we will assume that VC0 minus is 0 volt. Okay, so let's see how we can derive it. Okay, after T equals 0, the switch going up. Okay, so which means that when T is larger than 0, the switch going to the upper position, going to node A. When T is 0 plus, it goes to node A. Okay, so this EMF will connect to the RC circuit. Okay, and the current will be like an exponential function. The voltage is like a constant minus, okay, still an exponential function. And then here we have a RC to be the time constant. And as I mentioned, RC is like somewhere here. RC. this might be the tau equals RC, which means that it goes up from here to here. Let's say if this one is 0, this is 1, the height of RC will be like 0.6, I forgot the value, 0.628, okay, 6, yeah, 628. Okay. So let's see how we can derive it. Here we have the E, we have the R, we have the C. Suppose this is T is larger than or equal to 0. This is C. Okay. And then also we assume the current is I. And then we also have the initial condition or the initial value or the initial value or initial condition to be VC 0 minus to be 0 volt. And then I hope you still remember only the voltage of a capacitor must be continuous. The current might not be continuous. Okay, so here we can quickly write that VC 0 plus is also 0 volt. Okay, so this is actually the initial condition. Okay, so here we try to use the KVL, use the KVL to write an equation describing the circuit. Okay, so let's say let's start from the ground node and then going to here. So we will have a battery, which is like the input, the G of T on the right side of the differential equation. Okay, so here I cross out, I times out is I out, and then plus. Okay, so this is I here. Okay, so here we should have VC, or maybe we can just write it as we can just write as VC. So what is the relationship between the I of the capacitor and the voltage across the capacitor? So I hope you still remember it is actually C equals C dVc dt. I equals C dVc dt for this part. Okay, so this is actually, if you just write the KVL, this part should be VC, so from higher voltage to lower voltage, so we should have plus VC. Okay, so here we know that I is actually this one. We can just plug in this one to here. I equals C dVc dt. So we have C dVc dt multiplied by R. Let's just put it in the front, and then plus VC equals E. Okay, so we can just divide both sides by RC. Okay, so we will have dVc dt plus 1 over RC VC equals E over RC. Okay, so this is a first order constant coefficient ODE. The coefficient 1 over RC, both of them are constant. So this is a constant coefficient linear ODE. Okay, so first step is to write the characteristic equation. This is the first derivative, we change it to S, and then plus 1 over RC is a constant, and then VC we change it to 1, and then equals 0. So we can quickly find that S is negative 1 over RC. Okay, which means that VC, the complementary solution should be A times exponential to negative T over RC. If you still remember, it corresponds to the solution exponential to ST. Okay, so you plug S to there, so it will be negative T over RC, and then of course multiply by a constant because it is linear. Okay, and then for VCP, the particular solution, it is related to this constant. So VCP should be another constant, let's say B, and then we can just plug in B back to here, so the or we can just put it back to this one, okay. So the first derivative of VC will be a 0, okay. Derivative of a constant is 0, so we should have 0 plus 1 over RC times B equals E over RC. So we can just cancel RC on both sides. We can quickly find that B equals E. So the complete solution VC will be VCC plus VCP, which is E plus A exponential to negative T over RC. Okay, so finally we need to determine A. Okay, so actually, hope you still remember we have the initial condition, which means that we can just plug in 0. VC 0 plus will be E plus A, and then exponential to 0 will be 1. So this is it, and then equals to 0. So we have A equals to negative E, and then we can plug in this one back to here. So finally, VC will be E times 1 minus exponential to negative E to the negative T over RC. Okay, so this is the solution. We get this expression. Of course, you can just define RC to be tau, and then you can just make it like VC to be E times 1 minus exponential to negative T over tau. This is the time constant, or actually this one, I equals E over R exponential to negative T over tau. Depends on whether you still write it as a negative T over RC or negative T over tau. Okay, so we get this one first, and then still we can be able to get I. So for the I is actually CD VC dt, and then also we have VC to be E times 1 minus exponential to negative T over RC, like this. So we can just plug it here. So C, and then dVC dt. This is a constant. We can just put it to the front, and then this is a constant. When we take derivative, it becomes 0. Okay, so this one vanish. Okay, so for this one, we have exponential function. So the derivative will be itself negative E times negative E to the negative T over RC. And then don't forget the chain rule. We need to take the derivative of the exponent. Okay, the derivative of the exponent, this is a first order polynomial. So this become a constant, negative 1 over RC, like this. Okay, so altogether we can just do some cancellation. This is negative sign, so it becomes a positive sign, and then C and C can cancel each other. So finally we have E over R, and then the remaining is this stuff, E to the negative T over RC. Okay, so this is I. Actually the same as this one. Okay, so that's why we need to know how to solve the constant coefficient ODE. Otherwise, we may not be able to know why it be like that. Okay, so next part is, okay, so after this situation, it is just like so actually, when you just ignore this complicated equation, it will be just like, finally this voltage will go up to E as this one. This is E. Finally it will go to E. Because this is exponential. This is exponential decay. So the current will be something like this, exponentially decay. But for the voltage, yeah, it just draw Q here, but actually V will be similar, but with a different axis. So with the V, it will be like this is E. So which means that the voltage across the capacitor will charge from 0 to let's say to E, okay, to finally to be E, something like this. But it takes time. It takes time. It depends on how large this RC is. If RC is large, then it will be slower. If RC is small, it will be quicker to settle at this point. Settle. Okay, so for this situation, it means that now the capacitor is fully charged to a potential, let's say V0 or E. Okay, so at a new time, okay, so we just call that one to be V0, okay, V0. At a new time T0, at a new time so at the new time T is smaller than 0, the switch connect to A, okay, after a long time, which means that VC 0 minus is actually V0. And then at T equals 0, the switch go to the node B. Okay, so in that case, the charge here will start to discharge. Okay, there will be charge here, and then it will start to discharge. Okay, and then it tells you that the current I will be like this. Okay, of course it still remain I to be in that direction, so I to be negative value, and then VC will be like exponential decay. So we can still derive this one, and actually it is easier because we only have RC in series, but it connects to nothing else. Of course, we have VC here, and then VC 0 minus will be V0 equals VC 0 plus, because the voltage of a capacitor must be continuous. Okay, we still have I in this direction. Okay, so still we use the KVL to write the equation. Okay, so here start from the ground node and then going to here, I times R, and then if you still remember, I is nothing but C d VC dt, and then from here to here, higher to lower, so we have a plus VC equals 0. We have no battery at this case. Okay, so let's divide let's divide RC on both sides, so we have dVC dt plus 1 over RC VC equals 0. Okay, so this is actually the same as the previous one, but on the right side we only have a 0, so we can quickly find that VC to be A times exponential to negative T over RC. We don't have the particular solution. The particular solution is 0. Okay, so we can just plug in the initial value. VC 0 plus to be A, to the exponential to 0 is 1, so A times 1 to be V0. So we can quickly find that A to be V0. So the VC will be V0 exponential to negative T over RC, which is actually this one. And for the I, we can also find it quickly. I will be C dVC dt. So C, and then we plug in this one here. So we have V0 and then exponential to negative T over RC, and then also the chain rule, this part. So it will be negative 1 over RC, like this. Okay, so we can also cancel this C and C. So finally we will get negative r, v0 over r, and then exponential to negative t over rc, which is actually this one. Okay, so here we have finished off chapter 27.